In 2005, NASA created the Ares Projects Office as part of the Constellation program to develop new launch vehicles to take crews and cargo to Earth orbit, the Moon, and beyond. The Ares projects leverage 50 years of space transportation design experience and hardware to provide America once again with the space exploration capability it needs to move beyond Earth's orbit. To take astronauts to the Moon, the Ares 5 heavy lift cargo vehicle launches first, carrying the Altair lunar lander and the Earth departure stage, or EDS, to low Earth orbit. The Ares 5 uses two 5.5 segment solid rocket boosters, evolved from the current 4-segment design used by the Space Shuttle. The core stage also includes 6 RS-68 engines, upgraded from the version in use today on the Delta IV cargo vehicle. The Earth departure stage, powered by a J2X engine derived from the Apollo J2 design, makes the final push to orbit, where the EDS and Altair will await the crew. The Ares 1 will launch soon after, carrying its crew of 4 to orbit in the Orion Crew Exploration Vehicle. The Ares 1 first stage uses a 5-segment solid rocket booster, similar to those used on the Ares 5, and an upper stage powered by the same J2X engine used on the EDS. Once in orbit, the Orion will dock with the Altair and EDS. When all systems have been checked out, the EDS will fire its J2X engine to send the crew onto the Moon. To undertake a task of such magnitude, Ares draws on experience from across all the NASA centers. In addition, a strong industry team including ATK, Boeing, and Pratt & Whitney Rocketdyne is supported by subcontractors and hardware vendors from across the United States. The Ares vehicles are America's rockets in more ways than one. The task of overseeing and integrating this nationwide team falls to the Ares Vehicle Integration Office. This is a government-led effort employing civil servants and support contractors to perform integrated vehicle design and analysis. The System Integration Laboratory is the primary facility for the initial integration of the Ares 1 avionics and flight software systems. Here, project engineers get their first look at a real-time simulation of the Ares 1 ascent trajectory. Marshall engineers monitored the simulated flight, examining different physical properties of the vehicle during its ascent. Data on pressure, altitude, and velocity are input into the simulation to help the vehicle designers optimize the configuration of the vehicle's electronics and software systems. Computer simulations were also used to aid vehicle designers in understanding possible abort and mishap scenarios. Researchers examined possible debris impacts with the Orion crew vehicle in the event of an Ares 1 mishap. The team also studied blast wave behavior in the event of an Ares 1 failure to determine what effects such a blast would have on the Orion crew vehicle. This helps engineers design the vehicle's launch abort system, which will carry the Orion away from danger in the event of problems during flight. In Boeing's Polysonic Wind Tunnel and the Langley Research Center's Transonic Wind Tunnel, extensive testing has been done on 1% scale models of the Ares 1. Using a series of models of increasing fidelity, engineers gathered massive amounts of data on the aerodynamic and thermal environments that Ares 1 will encounter as it rockets out of the atmosphere and into Earth orbit. A larger model has also been tested at Langley. This model was fitted with more than 250 pressure sensors to gather environmental force data at specific locations on the vehicle structure. Ascent isn't the only concern for the wind tunnel teams, however. Another series of tests examine the forces affecting the first stage during its re-entry. Engineers are using this data to design the first stage thermal protection system. One of the more critical moments in the Ares 1 flight is stage separation, when the first stage booster is jettisoned and the J2X engine is ignited. Extensive wind tunnel testing has been conducted to gain data on this event, using both small and large-scale models. Wind can also affect a rocket prior to launch, so engineers are studying the effects of ground-level winds on the vehicle as it rolls to the launch site and while it sits on the launch pad. To date, more than 7,000 hours of wind tunnel tests have been conducted, covering all aspects of Ares 1 operation, from resting on the launch pad to ascent to separation of the first and upper stages. Progress is also being made towards full-scale hardware testing of the Ares 1 hardware. Marshall's Dynamic Test Stand, originally built for vibration testing during the Apollo program and later used in developing the Space Shuttle, is currently undergoing refurbishment to serve in a similar capacity for the Ares 1. The renovation of this facility, designated a National Historic Landmark, is scheduled for completion in 2010, and it will be used for ground vibration testing of full-scale Ares 1 hardware starting in 2011. In addition to its work on integrated vehicle testing, the Vehicle Integration Team has been responsible for ushering the Ares 1 vehicle design through a series of rigorous design reviews. Progressing from the System Requirements Review in 2006 to the System Definition Review in 2007, the team most recently completed the Ares 1 Preliminary Design Review, or PDR. The 31-member PDR board voted unanimously in September 2008 to proceed with the project's detailed design. The next step in this process is the Critical Design Review, scheduled for spring 2011. Completing that review will mark the transition of the Ares 1 from the design phase into the development phase, where focus shifts to manufacturing flight hardware and preparing for full operations. The Ares 1 first stage element draws on more than 20 years of NASA experience with flying solid rocket boosters as part of the Space Shuttle program. Work is well underway on extending these solid rockets to the 5-segment version required for Ares 1 and the 5.5-segment version needed for Ares 5. The team is also implementing improvements in technology and materials to increase both vehicle performance and safety. Ares has worked with the Space Shuttle program to add test objectives and monitoring equipment to already planned shuttle booster tests in order to gather data for Ares 1 use. Several such test firings have been conducted already, providing Ares engineers with valuable data about motor acoustics, roll torque, and new insulation and O-ring materials. Ares has also placed instrumentation on recent Space Shuttle flights to measure solid rocket booster thrust oscillation. A new asbestos-free motor insulation material will improve worker safety and reduce processing time for the first stage. And the new O-ring material, using carbon fiber rope, will streamline processing and assembly operations. The larger booster, higher speed, and increased altitude of the Ares 1 during booster separation demand an improved parachute recovery system as well. The first stage will use a 3-stage system, with pilot and drogue parachutes preceding the 150-foot diameter main parachutes. In the final vehicle, it will require 3 of these main parachutes to slow down the first stage prior to splashdown in the Atlantic Ocean. Fabrication is underway on these main parachutes, the largest ever deployed, in advance of a cluster drop test next year, where all 3 main parachutes will be deployed together for the first time. The integrated parachute system will also be used for the Ares 1X flight. Process testing is underway for the first stage's demonstration Motor 1, the first full-scale version of the Ares 1 first stage hardware. Workers have completed initial fabrication and test assembly of the first stage nozzle, as well as casting of the forward segment with inert propellant. These test articles paved the way for the demonstration motor construction in 2009. As part of this work, the team has also been testing new manufacturing and handling operations that will greatly increase worker safety when handling live propellant mixtures. Taking the Ares 1 on the second phase of its journey from Earth will be the spacecraft's upper stage, powered by the J2X engine. The Ares 1 upper stage is approximately 18 feet in diameter and 84 feet long. A series of confidence panels have been tested to verify the structural characteristics of the upper stage aluminum-lithium materials. These tests also determine the ideal thickness of the metal panels that will form the barrel of the upper stage tank. Starting with smaller panels than will be used for final flight hardware, the team was able to optimize the panel strength and thickness while keeping the weight of each panel as low as possible, maximizing the vehicle's payload capacity. Full-size panels have since been fabricated and delivered for final assembly and testing. In addition to the tank barrels, engineers have fabricated curved gore panels that will form the fuel tank's domes. These gore panels are initially stretched into shape from flat pieces of metal and then heat-cured. Once cured, the panels are coated with a masking material and then subjected to a series of dips in a caustic chemical bath. This chemical treatment mills the panels to a uniform thickness across the entire panel.